You understand?
Yeah, let's start.
Okay.
We start with the cube, Professor Mourik, the first big three-state quantum device.
Right. Next slide. Try to be so entertaining and don't fall asleep. All right. This is the last lecture today. It's more about, given that we have these nuclear spin systems that we can control using devices or electronic devices on chip, what can we do with them? So again, so it's a little bit of a mashup, I would say, like short, distinct topics, probably about half an hour each or so, and one of them will be presented by Sebastian, because this is master thesis research. I think it's nice when he presents his own work rather than that I do that. All right. So this was, I just found when preparing for my slides today, I found somewhere in a very old presentation this beautiful animation that I should have showed you yesterday, so I will show it to you now as a refresher. So, needs to play, of course. So this is the device that we're having. We have the SET sitting over here. That's our charge detector. We have a donor here. We can apply electric fields to it. And we have the static magnetic field. We have this manifold here of the nuclear spins. So the nuclear spin is in a given state. We load an electron. We apply a pulse, of in this case the yellow frequency. And here we can flip the electron spin. And then we can do the conditional readout. Here we manage to flip it and we get tunnel current. But then in the case when we apply the other pulse, so in this case the green pulse, and we can't flip the nuclear spin because it is in this subspace, then we have also projected the nuclear spin by not observing this little readout. So that was the general operational principle behind all these measurements. This is single-shot readout of a nuclear spin, and then when you can do all the pulses, etc., you can construct radio oscillations, all the pulses, etc., that you need for spin control. So, this is the spectrum that we were dealing with. We had all these levels split in a manifold of spin down, electron spin down, and electron spin up, and then we have 8 levels of the nuclear spin, and we have this whole zoo of transitions, basically, that we can characterize and access and use for coherent control. That is what I showed you yesterday, that we have that capability and that this is a very coherent object with lifetimes of about 0.1 seconds or so, and without any dynamical decoupling. And yeah, we can do order 10 to the 4 pi pulses or so on this type of system. This is the interesting interaction from a physics perspective. I would say the Zeeman interaction is well known. Van interaction in these type of systems, I think, is relatively unknown and unexplored. And a lot of what we discussed today will be about the details of this interaction too. All right. Oops. There's a whole bunch of animations still. So, what do we have? Quantum K, more quantum Ks. Okay. Some recent results that just appeared on the archive a few weeks ago. Then Sebastian will talk about mechanics, and at the end, I want to talk a little bit about replacing the donor electron spin with a quantum dot electron spin, because it has some other attractive aspects to it. So, I know that you got like super complicated chaos theory on condensed matter systems, etc. I think it's marvelous theory. I struggle understanding of it myself. So what I'm going to give you here, like as a courtesy to experimental folks maybe, is my take at quantum chaos from the perspective of an experimentalist. Also, it is from the perspective of a single particle, because a lot of the quantum chaos work is done on big ensembles or on condensed matter systems, etc. This is single particle dynamics I want to discuss, right? Because we have a single degree of freedom. So this, this you all know, I presume, like you got this at some point during undergrad graduate school, that in classical dynamics we have the concept of a phase space. In phase space we have a distinct initial condition. We have trajectories in phase space when we solve the dynamics. And we have the equations of motion. And then one way to view different initial conditions is by having slightly different axes with different trajectories of such a system. All right? That is classical. Now, chaos, of course it's hard to give, like people disagree a little bit what is the best definition, but this is a good working definition that I got from, I think, Strogat's textbook on dynamics. It's a nice definition, I feel. Aperiodic, so it's non-periodic, long-term behavior in a fully deterministic system, right? We know the equations exactly, exhibiting sensitive dependence on initial conditions. Okay, so initial conditions, you perturb them a little bit, you get aperiodic behavior. And it's very sensitive to that. That is, I think, how you can view chaos. And then this is sort of like, more mathematically, we have a thing called the Lyapunov exponent. That is the distance between two trajectories, and what you will see, that is another more mathematical definition, is chaos, that trajectories diverge exponentially fast in time. Now, quantum dynamics, you can, of course, try to think about all these concepts as well. So we have now the Hilbert space. We have a wave function, which is a probability density function. We have the Heisenberg uncertainty principle. We have the Schrödinger equation, and we have unitary time evolution. Okay? So what this means is that initial condition in quantum mechanics is now no longer an exact point. It is an uncertainty wave package with a Heisenberg spread around it. That means that the whole concept of phase space, of course, we have non-commuting variables and all that, it doesn't copy well to quantum mechanics, which is why it's an interesting thing to consider. And a trajectory, we can still think of a trajectory in a phase space that would be quantum, but it's no longer a sharp line, no, it's a blurred sort of behavior in the phase space, in the corresponding classical phase space. So, this is a bit trivial, but I think it's still nice to show. You do the same game you do classically in quantum mechanics and the unitary time evolution, because this is all linear. We can do this little exercise, two wave functions. We have one wave function phi, and then psi 1 and psi 2. That has a tiny bit of a component of an orthogonal state from the eigenbasis, and you evolve this under time. You will see this is just a trivial little bit of calculating. I love that I can say that we're trivial about the calculation as an experimentalist. Anyway, but this is really simple. The point is that the distance between these wave functions, or the overlap between these wave functions, stays constant in time. Right? By definition, in the unitary time evolution. But begs the question, of course, like, is there no chaos in quantum mechanics? And if you look at this, then in a way there is no chaos. It's not the same as classical, at least. And this is the wrong way to think about chaos, both if you want to compare the two, I would argue. Because you need to think in it in terms of phase-space volumes. The Liouville operator and formalism is there important. So you have now a phase-space density, so we don't look at a single classical initial condition, but we look at a little void in the phase space. And you evolve that under the classical equations of motions, and then there is an old famous theorem that actually the overlap between two classical phase space densities, so a little void in phase space and its initial overlap, that also stays constant classically. So in that sense, this picture can be easily reconciled. Now, the real difference is that, well, phase space volume is conserved classically when you evolve it under time. It can get a crazy shape, and that is what chaos does. So initially, a little square in phase space initially can evolve into some crazy shape that is very flat in one direction and expands really a lot in another direction. And you get all these rich features in there. And that is, of course, we know all these beautiful examples of turbulence and chaotic behavior. Fluid dynamics is very rich in all that. And that is where I think the interesting question is, that's really at the heart of the difference between classical and quantum nonlinear dynamics. This is, I think, this is the original paper where this was first, I think, sort of clearly put forward. So it's by Michael Berry and Koch. So on this axis, you go from quantum, so h bar has a finite value, and you put it to 0. So the system becomes less quantum mechanical. And on this axis, I think they increase the nonlinearity of the system. And this is a nonlinear pendulum of some sort. So one axis is momentum, and the other one is the x-coordinate. And what you can see is that in the more nonlinear case, where it's more chaotic, in the classical case, you have these sort of tendrils that you get in the phase plot. So the classical system behaves chaotically. But the work of h bar, of the uncertainty principle, is to smooth all this out. So you lose this in deep quantum limit, where you have a very small isolated quantum system. Now, on the other hand, this is a more recent work by Usageand. You do get interesting quantum interference phenomena again when you have states, quantum states that are classically chaotic, and you let them interfere with each other. You can get crazy interference patterns that are actually much smaller than small on the scale, on the Planck scale, on the scale of h bar. I don't know if how easily you can measure this, but at least I think this is how I understand this paper, that this is a reappearance actually of finer structure in quantum mechanics. Now, from an experimental view, this is a very rich field. This field got sort of, this 1981 paper, I think, is sort of the first paper. It's about 10, 15 years after the discovery of classical chaos. People started thinking about quantum chaos. Very rich field, by now like 40 years of theory research, and actually, up until quite recent, I don't think there are that many experiments to consider. Because this is quantum dynamics that you need to understand in great fine detail. And that was just very difficult until recent. So the best people could do until about the late 90s, early 2000s was look actually at the spectrum of a quantum system, sort of a larger quantum system that's sort of going towards the semi-classical limit. And one, I think, interesting example is these large, they were called quantum billiards. So this is in a two-dimensional electron gas. You make a quantum dot, but you make it rather large on purpose, and you play with the shape of it. You get many quantum dot levels in there, and you look at the level statistics as a function of, I think magnetic field it was, how these levels behave. I don't know all the details, you would have to look that up. In any case, there is some sort of correspondence that you can say certain statistical distributions of these quantum dot levels indicate that you may have a chaotic billiard. So this is an irregular one and this is a chaotic one, where the levels are chaotically distributed in this quantum billiard. And honestly, I think up until the late 90s, this was kind of the best experiment there was. Very indirect connection between chaos and quantum mechanics. This is, I think, one of the first experiments that sort of like, it's not quite chaos that they were studying here, but they were looking at least non-classical, nonlinear dynamics. So what happens here is that this is a system where they have a classical phase space, which is mostly chaotic, but it has some regular regions in there. So this is in optics, in a cold atom ensemble. So they implemented some form of a kicked rotor, I think. In any case, what happens here is that classically, once you are in a regular region, you have to stay in a regular region. Okay? So an initial condition that has one closed regular trajectory around it, you will know it will always remain a regular trajectory confined within the outermost region. This is a famous theorem. I'm formulating it a bit hand-wavy here, but this is the KAM theorem. And crossing, the point is that crossing between regular regions, like crossing through a chaotic region, is not possible classically, because it would mean non-uniqueness of your solutions, basically. Quantum mechanically, this is not the case. You can actually, because you don't have exact confinement in phase space, you can leak out into the chaotic region, and in fact you can have tunneling between these regions. And this is called dynamical tunneling. So it is a tunneling process, but it is not through an energy barrier, it is through a phase space barrier, if you wish. So it's a quantum mechanical violation of this theorem. This was the first time this was observed in a cold atom ensemble. It was, I think, quite a, the data isn't all great looking, but yeah, it was quite an important experiment, I feel. It's of course difficult because ensembles, your Hamiltonians are much more approximate. You have interactions, etc., in the ensemble that you sort of disregard. But when we look at subtle dynamics, this is tricky because sort of they are probably small correction terms to your relevant equations of motions that you disregard. That is, I think, why it's so nice to have a single degree of freedom in the case of this nuclear spin, for example, where you know the equations very well. This example I like, because what this is, I should draw this on the board, this is basically a triangle of three superconducting qubits. So you have qubit 1, qubit 2, qubit 3. And there is, they are coupled in this triangular shape, and you can play with the coupling strength between them. And by playing some clever tricks, you can implement a chaotic Hamiltonian, a classically chaotic Hamiltonian on this one. And the way they measure that is that they prepare initial states that are pure states on each individual qubit. So this is a fully pure subspace of a spin-1/2-like particle, basically, in each superconducting qubit. And then by letting time evolve under a specific Hamiltonian, you see that the pure state disappears, and basically, as time evolves, you create an entangled state across this entire cluster of three qubits. And what this means is that the entropy of the individual qubits has increased, and yet just through the dynamics of the system, by implementing nonlinear Hamiltonian, you create entanglement. And the funny thing is that this depends on the initial conditions that you choose and what exact Hamiltonian you implement. So you can sort of map out a classical phase space again. You get high entanglement entropy in the system for classical initial conditions that would be chaotic, and you get low entanglement entropy for classical conditions that would be regular. That's the point of this paper. That's by now in 2016, so it's a few years ago. I think it was sort of the first type of these experiments in a condensed matter qubit system. Of course, by now Google is utilizing similar principles to be able to explore rapidly the entire Hilbert space of its many qubits processor, etc. That is also related to chaotic scrambling, but it's very, the scrambling in a quantum system is quite related to chaos in the classical system. So similar principles are behind Google's approach to create entanglement across their entire cluster of qubits. Okay, so we can implement a classically chaotic system on these nuclear spins. And the model system here is the kick-top. Anybody that has ever looked into a quantum chaos knows that this is really the model system in that field. Kicked rotor. And the idea is that you have like the spinning top that you have, but now there is another axis along which you perturb it with a nonlinear interaction too. So it's like sort of natural to think of this as a spin as well. You have a precession along one axis, and then along an orthogonal axis you have another precession, and that needs to be a nonlinear one, and then you perturb it. So you give it little kicks basically. That is why it's called the kicked top or the kicked rotor. And you implement this system the right way. You can draw the phase plots. You can see that you can have mixed phase spaces, make it fully chaotic, make it fully regular, depending on the parameters of the system that you choose. Actually, it is quite an important system even today in the context of quantum computing. Because digital quantum simulations, you can map it onto the dynamics of this system, this model system. And yeah, digital quantum simulations, it involves the totalization of quantum algorithms. And the coarser you do that, the larger your error growth. And it turns out that this growth of error in this process maps onto the dynamics of the periodic dynamics of the T-top. So it's quite nice that yeah, these sort of old model systems are now finding applications again in the theory of quantum computing, I think. In any case, I'm of course not a real expert on all the theory ins and outs of these works, so please, if you find this interesting, look these papers up yourself and study them. There are very few experimental direct realizations of this system. The best there is in a cold atom ensemble in 2009, I think. But it's the direct attempt to realize this system. Then there is this one here. I'm not really aware of many other experimental implementations. So how does the Hamiltonian look like? So we slightly, in many of the theory papers, this term here is a train of delta pulses, but yeah, we do spin resonance, so that is for us, a sine or a cosine is much easier, that is why we call it the driven top. But the classical Hamiltonian looks like this. You have a linear angular momentum operator, a quadratic angular momentum operator, and you have another one with a periodic drive. Those two need to be more or less orthogonal. This one doesn't matter so much, but the details of the dynamics change a little bit if you put this along a different axis. Of course, you recognize here more or less the shape of the quantum Hamiltonian that I showed you before of these large nuclear spins. We have the Zeeman term here that can implement the LZ. We have the counterpole term here that can implement the orthogonal quadratic interaction, and we have the spin resonance term that can do the periodic perturbation. Okay? That's the idea behind this type of research. Now, this I showed you already, that we have all these transitions in the system and we can really uniquely address it. And now it becomes a game of playing with the strength of these two interactions to make them of more or less equal size, so that we can reach dynamical regimes that are chaotic or regular or mixed phase spaces, etc. Now, we did, of course, a bunch of simulations. Of course, it's like when you propose something, you always conclude that it's possible, so it's possible. It's hard, but we can implement this, we think, on one of these bits, this model. The hard part is that the Zeeman interaction typically is of the order of 1 megahertz. And this interaction, you may remember that from yesterday, is more of the order of 60 kilohertz or 50 kilohertz. So we are a factor 20 of or so, and that would be too much to create chaos. Then you can play a trick, so this is a little bit of trickery that you can do, go to the rotating frame. So you do some, from an experimental viewpoint, it is not all that hard, IQ modulation and some extra amplitude modulation. But in any case, you implement this type of periodic perturbation. You have this continuously on in the background, and then you transform it to the rotating frame and apply the rotating wave approximation. You have cancelled out this strong linear term, the static linear term, and now your linear interaction is given by the drive strengths that you have. And that should be more than enough to, it might be possible to do it in a direct fashion, and otherwise we can play this to implement the Hamiltonian. Yeah. That is the point here. Now I want to take a tiny detour. I think it is necessary. If you're familiar with quantum optics, you know the concept of a coherent state. In spins, it's a little bit more tricky, but we can define a similar concept of a spin coherent state. For spin 1/2, we never worry about this, but for larger spins, it is actually a very useful concept to know. So what is a coherent state? It is a state that is a minimum uncertainty state. It is minimal, it's like really the minimal uncertainty spread that you can have. So it has a bunch of properties. For example, it satisfies the maximum spin length. So how you can view it is that you have, for this 7.5 spin, you have its ground state plus 7.5, And now you're actually in real space geometrically rotating this state around, and this is a minimum uncertainty package that you can point in any possible direction. That is what spin coherent states are. Okay, so it's a spin state pointing in real space into any arbitrary direction, keeping its minimum uncertainty spread. Yeah. So we can visualize this. The more famous one is the Wigner phase space representation. I will show later in the presentation a few examples of that. Another one that you can use is the Q representation, or the Usageand Q function. This is also, I think, quite a nice one. And basically, when we are working with an 8-dimensional, higher dimensional object, so we need to look for new visualization techniques, right? Like for spin 1/2, we have the blob sphere, which is super convenient, but we no longer have that when we work with a large spin. So this is one way to do that. And I kind of like this one for this part of the story because it is the closest you can get to a classical phase space representation. So these Wigner function and Usageand function, they're called quasi probability density functions because they don't satisfy all the proper definitions of a real probability density function, but it's the closest you can get in quantum mechanics. The Wigner function is non-classical because it goes negative. This one is non-classical because it's not uniquely defined everywhere. In any case. So the way you construct this one is you have an arbitrary wave function of this spin, and you take the inner product with all the coherent spin states. So these, you overlap it with these spin coherent states. So if you now take a coherent state, so on these axes here we have the spin quantum number, you can see that the ground state of the system looks like something that is the function has a high value near the top here, and this is basically the size of this is the uncertainty spread of that spin around this value. And then another coherent state is this blob rotated in real space. Right? And this is why I like this coherent state, this type of representation, because now we can overlay this with the classical phase space of the system. So here we have the yellow-orange dots are chaotic trajectories, and the blue ones are a regular trajectory. And this is the same Hamiltonian that we implemented that I showed you earlier. And now you can see what the Planck constant actually does. So for a spin 1/2, your spin is possible to wander over the entire hemisphere, basically. So for a spin 1/2 system, all pure states are actually spin coherent states by definition. So it's nonsensical to consider a spin 1/2 system, apart from that you don't have nonlinear dynamics anyway, but yeah, you cannot confine it at all in corresponding classical phase states. What you see is as the quantum number grows, the quantum states, its uncertainty spread relative to the classical phase space becomes smaller and smaller. Okay, and for a really large hypothetical spin number, you can see that you start confining it, and by the time the spin quantum number reaches something like 1,000 or so, you have more or less a dot. Okay? So this is the game we want to play. This is where we can operate. So we're going to create spin coherent states that we point into different areas of the corresponding classical phase space. So we can prepare the equivalent of a classically regular state or a classically chaotic state and see what happens to the dynamics. So, and that is actually a way where you start recovering some signatures of chaos in the quantum system. As a first example, here we prepared a spin coherent state that originates in a classically chaotic region. And what you see there is, of course, this is an entirely closed system still. There's no decoherence in it whatsoever. But if you time evolve this initial state, so I'm plotting here the overlap with the initial state in the time evolve fund, you can see you have all these discrete frequencies in here. There's 8 of them in this system because it's an 8-dimensional Hilbert space. But you know, there's a pretty rapidly climb. Occasionally there are quite strong revivals where the state returns close to its initial position. But really, this becomes an aperiodic in a way. It never truly returns to its own original state. Now, what you're seeing here is scrambling. Scrambling of an initial state pretty fast through the entire quantum phase, through the entire Hilbert space of this spin. Okay? Mind you that this is not classical chaos, right? But we can link relatively fast scrambling of this spin to the chaos, classically chaotic regions. Now, conversely, when we sit in the classically regular region, we get dynamical tunneling. So now only one or two of the characteristic frequencies in the system have a high weight in the quantum system. And you get this nice, nearly sinusoidal, and it revives almost all the way back to the top. And this is dynamical tunneling of the quantum system between two classically regular regions. So classically this would not be possible. Of course, because we still have tiny weights of the other relevant frequencies in this system, you see that it doesn't truly revive all the way back to its original position. So these type of experiments we can now implement in this spin. Okay? Another interesting feature, I think, is how sensitive such a spin is now to decoherence. And this is, in our original paper, we did that in a very hand-wavy, sort of non-formal way. So what we did is we started with a spin coherent state, and we time evolved it, and we perturbed it along the way a little bit, and we looked what that did to the purity if you average over many trajectories. And what you can see is that the classical phase space here, you compare that with the purity of a quantum state that is evolved under perturbations, you can see that we start recovering the shape of the classical phase space here. It's not quite the same, but you can see that classically regular regions are regions of, that are less sensitive to decoherence. So this is basically saying that you scramble not as fast, whereas classically chaotic regions tend to be a bit more sensitive to decoherence. Now, we can do this also more formal. We've done that in a collaboration with theoreticians, Klaus Milmer's group in Aarhus, Denmark. And then you can define an out-of-time ordered correlator that we can measure in such a spin system, and that would then be a measure for scrambling and the influence of decoherence. But it's in essence the same idea. All right. So these are ideas that we want to do. This was actually what I started my postdoc with in Sydney. I spent the first half year, 1 year or so doing these simulations, working out like, can we do this experiment or not on these nuclear spins. That was sort of the whole motivation behind the project. Start doing nonlinear quantum dynamics. And in parallel, we started implementing the experiment, and I showed you day before yesterday the first experimental results with that broken device. And now the group has actually gone further, of course, in a better device. And this is now the state of the art. I think this is a very exciting paper if you find this topic interesting. So this is from May, and they presented it for the first time at the March meeting, and now the paper is on the archive. If you like this topic, I invite you to read it. It's pretty well written, I must say. I'm of course no longer a co-author on this to pass my time. So first of all, what they do here, I show Wigner functions. Okay, so these are not the Usageand plots that I showed before with Wigner phase state representations. The first cool thing that they can do is they can create one of these spin coherent states, and actually it's basically mostly software trickery how you apply your pulses, but by applying multiple pulses simultaneously, you can now implement Pauli spin matrices rotations for the spin coherent state itself. So you're treating it like a spin 1/2 object and rotating it all through the 8-dimensional Hilbert space. So technically speaking, it is covariant as you do rotations of this spin. And they use this, and I think that is really cool, to create an equal superposition of two coherent states that sit at opposite poles of the hemispheres. Okay, and that we know as the Schrödinger cat state. So this is basically a maximally quantum state. This is as quantum as you can make a superposition state in the system. So this is the state they implemented. So this is The first experiment, this is experimental data. Here this is snapshots as they pulse the system, so you can see how they start here at the bottom, and then you get more and more weight higher up. And here this is the linear representation of this cat state. Okay? And here then, of course, when you have that and you have all these, this control over it, you can treat it like a spin-1/2 superposition basically. But keep in mind, this is an 8-dimensional superposition actually. And you can do a diffuse star measurement, do a Haneffer one, and see what you get. And yeah, of course, this is pretty slow to make these things. You can see that on the axis here. This is 10 milliseconds scale to create it. And these spins do equal here on the scale of tens of milliseconds. So you can see that, it's damn oscillation. But I think it's a really cool result. I'm very excited about this. So this is really a step forward from what I showed you yesterday, that you can do all the pulses and do the normal, all these transitions to coherent control over them. Now they're really exploiting and utilizing the full power, I would say, of the microwave control machinery to do cool quantum stuff. All right, here I plan the break. Is that too quick? Up to you. Like that's, I think that I plan Sebastian to step in, so we can. But then it's another 20 minutes or so. So I think it's better to have a little break here. Questions? Was this clear? This part of the research is really focused on looking into the intricacies of the quantum dynamics of one of these spins, given that it is nonlinear, and really try if you can learn something new. I think it is still quite timely given the Hilbert space sizes that we have at the moment. Yep.
How do you handle measure this out of time order per
I have to pull up the paper to do it exactly, but it's basically you let the system, normally an out of time ordered correlator means evolving your state forward, do something to it and evolve it backward, and then measure it. Here we came up with a protocol that you don't have to do it, you do only a forward evolution because it's hard to undo time evolution in the system. That is typically very difficult. Here we came up with a protocol that you do it only through forward evolution and a perturbation, and then you can still measure this quantity out of time ordered correlator. So really, from an experimental viewpoint, what it boils down to is having arbitrary state control, let it evolve, do some other pulses to it, and do a projective measurement. It's in the end a fairly simple protocol. But then you calculate a quantity based on those measurements that you can plot in one of these phase spaces, and you create plots that are very similar to this type of plot. Yeah. But good enough an answer? Like, you want to know the details, we have to walk through the paper basically. Because then it becomes a little bit more technical. I think it's a nice protocol that works, that should work for these things. Other questions? Yeah.
I'm thinking about the kind of gates and what are you can usually in optics, because you need in the space that you have some Gaussian operators like the one that gave coherent states, cut states, which are simple to do, and then non-linear operations which are harder. Is there something like that also for this kind of controller, or is making like a cubic spin state as easy as making the coherent state because you're less
I don't want to give really exact answer on the spot, but definitely there are certain operations. I think the system isn't any different from an optical system, and you can already see that certain type of operations and protocols to create certain superposition states are much more natural for a spin system than other ways. So for example, here in this paper they show two different ways to create these cat states. One is by implementing these effective SU2 operations, and that seems to work a bit better than other ways. So I would maybe return the question in the sense that we have the system now, and we can also start thinking basically how to do cool things with it. But I think your intuition is correct. It should be possible to come up with certain type of state preparation methods, etc., experiments that are really natural to this type of control that you have, and others will be very hard.
It could be really cool if there was a natural way to implement an operation.
So
It would be really cool to have a natural way to implement an operation, so that you could then have like an universal gate set, which is kind of efficient.
Yeah. More questions, remarks? Otherwise, let's give a quick break and then Sebastian can take over. Is that okay? We return in like 5 past. Yeah.
Yes.
Yeah.